Okay, so when you hear the term programming language, Python, JavaScript, C++, what comes to mind? Probably a tool, right? Something you use to tell a computer what to do. And look, you're not wrong, but that's really only half the story. What if I told you that every single programming language is actually its own conceptual universe, a whole self-contained system just for thinking?
You see, this quote from computer science pioneer Alan Perlis, this is the key to everything we're talking about today. A conceptual universe. Think about that. It means the language you pick doesn't just let you write code. No, it fundamentally shapes the way you think about the problem you're trying to solve. It gives you this whole new framework, a new mental model to work with. All right, so if a language really is a universe, then what holds it all together? Just like our universe has fundamental laws like gravity, every single programming language is built on a handful of core principles that define everything you can do inside of it. So let's do it. Let's deconstruct these laws of physics for code. These are the absolute essential building blocks that designers use to create these universes, and they're the rules that we, as programmers, have to master to get anything done in them. And here's the wild part. You might think there'd be dozens, but there are only 4. That's it. Just 4. From the oldest languages you can imagine to the most cutting-edge ones being invented right now, they all boil down to these same 4 fundamental properties.
And here they are: syntax, names, types, and semantics. That's the list. Every single feature of any language, from the simplest hello world to the most mind-bendingly complex algorithm, is just a unique mix of how its creators decided to handle these 4 things. So let's break them down, one by one.
Okay, first up is syntax. And this one is probably the easiest to get your head around. Just think of it as the grammar and spelling of the language. Seriously, it's the set of rules that tells you how to arrange all the symbols and keywords so that you're writing valid statements. If you forget a semicolon or you misspell a command, bam, you've got yourself a syntax error. So syntax is what answers these really basic questions, like why does Python care so much about indentation while JavaScript uses all those curly braces? That's a syntax choice. It defines the whole look and feel of a language, and it gives the computer the strict rules it needs to even begin to understand what we're trying to say. All right, number 2 on our list, names. This one is all about how we label things in our code. I mean, think about it. Whether it's a simple little variable holding a number or a massive, complex function doing a ton of work, we have to give it a name. Why? So we can refer to it, use it, and change it later. Without names, our programs would just be an impossible, unmanageable mess. But here's the thing, a name isn't just a simple label you slap on something. Oh no, it's governed by its own little set of rules. For instance, every name has a scope, which basically defines where in the program you can actually see and use it. And it has a lifetime, which says how long that name even exists. These rules are absolutely crucial for preventing confusion and keeping our big, complex programs from turning into chaos. And that brings us to our third law of physics, types. A type is basically a category of data. It tells the computer what kind of information a value is. Are we talking about a whole number, a letter, or just a simple true or false? And just as important, it tells you what you can do with it, right? You can add 2 numbers together. That makes sense. But you can't really add the names of 2 cities together in the same way. The type prevents that. And you can think about types on 2 different levels. First, you have your simple kind of atomic types, like a single number or a single character. But then, and this is where it gets powerful, you can combine those simple atoms to build more complex, structured types. It's like building molecules. You can make a string of characters to form a word or a whole list of numbers to hold a data set. It's all about building bigger things from smaller pieces. And finally, the big one. We arrive at semantics. Look, if syntax is the grammar, then semantics is the meaning. This is the soul of the language, right here. It defines what the code actually tells the computer to do. It's the difference between a sentence that's grammatically correct but total nonsense and one that gives a clear, powerful instruction. Yeah, semantics is really where the action is. When I write a single line of code, what is the actual effect it has on the computer's memory? What behavior does it create? This is the most important property of them all because it defines what our code actually does. The whole point of writing the program in the first place. Okay, so we've got our 4 universal laws: syntax, names, types, and semantics. Now let's see how you can combine them in different ways to create wildly different styles of universes, which in the world of programming we call paradigms.
Now, a programming paradigm isn't just some technical feature or a buzzword. The definition says it's a pattern of problem-solving thought. It's a whole philosophy for how to structure a program, how to attack a problem. Using a different paradigm it's like switching from writing a super detailed step-by-step recipe to instead drawing a high-level architectural blueprint. Two totally different ways of thinking. And really, the entire history of software has been shaped by 4 of these major paradigms. Each one is a fundamentally different way of looking at a problem. But, and this is the cool part, they are all built using different combinations and interpretations of those same 4 core properties we just went over.
And just look at how different these mental models are. You've got imperative programming, which is basically that step-by-step recipe of commands. Then there's object-oriented, which sees the world as a bunch of digital objects sending messages to each other. Functional programming treats everything like a pure mathematical function. And then you have logic programming, which is completely different. You just describe the result you want and leave the how-to part up to the computer. 4 completely distinct universes of thought.
So why does any of this matter? Why have we gone so deep into the philosophy of code? Well, because understanding this stuff, it's about so much more than just learning how to write a program.
Here's the key takeaway, the most important point of all of this. When you learn a new programming language, especially one from a totally different paradigm, you are not just learning a new syntax. You are learning a new way to think. You're literally adding a new conceptual universe to your mind, giving you this brand new, incredibly powerful toolkit for solving problems of all kinds. And that leaves us with one last, really fascinating question to think about. If every language is truly its own universe for thought, built on these fundamental laws, then what amazing new ideas, what revolutionary solutions are just waiting out there to be discovered inside a language you haven't learned yet? What new thoughts could a whole new universe unlock for you?